In this problem, they're asking us to calculate how many moles are found in each of the samples. And in each case, actually in the first two cases, they're giving us a mass, and in the third case, they're giving us a number of molecules. So general strategy for part A, they give us mass in grams directly, so we'll just use the molar mass of iron 2 oxide, or iron 3 oxide, to get to moles. In part B, they give us mass in milligrams, so we'll first convert to grams and then use the molar mass of nitrogen dioxide. And then in part C, they give us molecules, so we'll just use Avogadro's number to get to moles. No need to find the molar mass of BF3 in order to solve the problem. So part A, my red number was 100 grams of iron 3 oxide. So I need to get the number of grams in a mole, which would be the molar mass. In order to do that, I've got to look up on the periodic table. So iron on the periodic table has an atomic weight of 55.8. And I double that because there's a subscript 2 for the iron. Again, I'm only carrying out calculations to the tenths place, because it's really not necessary to go in any more decimal places than that. So if we add together 111.6 and 48.0, I get 159.6 grams per mole. So what that allows us to do is tell us how many grams are equivalent to 1 mole. And then if you follow what happens to the units, grams of iron 3 oxide crosses out, and you're left with units of moles, which is what the problem wants you to arrive at anyway. So this one works out to be 0.62, and we're good to 4 sig figs here, so 6266 moles of iron 3 oxide. The next one, problem B, asks us about nitrogen dioxide, and they give us the number of milligrams. So 12.0 milligrams. The first thing I would do is convert from milligrams to grams. Milli means 1,000, 1/1000th. So 1 gram is equivalent to 1,000 milligrams. So milli is much smaller than a gram. The next conversion factor you need is one that allows you to go from grams of nitrogen dioxide to moles. And that would be the molar mass. So on the periodic table, if you look up nitrogen and oxygen, in this molecule there's 1 atom of nitrogen and its atomic weight is 14. There are 2 atoms of oxygen whose atomic weight is 16. And if we add those together, you would get 46.0. I only carry this out to the tenths place. So 46.0 grams per mole. We write that into the conversion factor, and if you look at the units, milligrams crosses out, grams will cross out. The unit that hasn't crossed out is the one that they want for your answer. Oops, I wrote NO3, I meant to write NO2 here. And it works out to be 2.61 times 10 to the -4th moles of NO2. when I go to type that into WebAssign, I'm just going to type 2.61 lowercase e and then -4. WebAssign will read that as 2.61 times 10 to the -4th. It's a nice quick way to enter that. Problem C, they give us not a mass but a number of molecules of BF3. So 1.4 times 10 to the 16th molecules of BF3. Now it could be molecules of anything. It doesn't matter what that thing is. Or even molecules. It could be a mole of anything has 6.022 times 10 to the 23rd numbers of that thing. In this case, it's molecules of BF3, but it could be, you could have a mole of pencils if you wanted to. So in this question, you don't even need to have the molar mass. You don't need to look up on the periodic table the atomic weights of B and F. If you follow the units, molecules crosses out, and you'll be left with moles of BF3, which is what they want. And so on my calculator, I'm taking 1.4 times 10 to the 16th, and I'm dividing that by Avogadro's number. And that works out to be 2.3, and I'm only good to 2 sig figs for this problem. 2.3 times 10 to the -8th moles of BF3. When I type that into WebAssign, I'll just put 2.3 lowercase e -8, and WebAssign will read that as 2.3 times 10 to the -8th.